All right. So, when you're prepping for the senior software engineer interviews, one thing that really kind of hits you is it's not just about like, memorizing algorithms and stuff. It's really about, demonstrating that you have a deep understanding of even like the basic concepts, right? The foundational stuff.
Oh, yeah, absolutely. Like you really got to know the why behind the what, right?
Yeah, exactly. And that's what we're going to tackle today. Something that might seem pretty basic at first glance. Java primitive data types, but trust me, like when you really get into it, there's a lot there, a lot that you can, uncover that really shows that senior level understanding.
For sure.
So we're going to be exploring the why behind these types, the subtle implications, and how the choices you make here can actually have a big impact on system design and performance, especially when you start talking about scale.
Yeah, and like you've probably been using, int and Boolean for years now. This isn't just a refresher. This is about understanding those nuances that really matter when you're operating at a senior level. How does this impact the bigger picture?
Yeah, exactly. And this is precisely the kind of discussion that's going to come up in those senior level technical interviews.
Without a doubt.
So let's dive right in. Let's start with assigned integer types. In Java, we've got 4: byte, short, int, and long. And at the most basic level, these are for representing whole numbers, both positive and negative.
Yeah, and each one comes with different storage requirements, right? So that means they have a different range of values they can actually hold. And while byte and short definitely have their place, int really is like the workhorse. It's that good balance between how much memory it takes up and the range of values that it can handle.
Yeah, that makes sense. You wouldn't use a byte to keep track of like the number of users on a huge social media platform, right?
No way. You'd hit that limit really fast.
But long, that's where it comes in handy when int just isn't enough.
Exactly. Like imagine your tracking website hits every second on like a global scale, and int would overflow so quickly. Or, timestamps with nanosecond precision. You need a long for that.
Yeah.
And this kind of leads right into those interview questions about scaling systems and the limitations that come with the data types you choose, especially as your data grows.
Right. And that kind of thinking, that forward thinking, that's a big part of being a senior engineer, right?
Yeah.
Anticipating those limitations and picking the right data type from the get-go.
Yeah.
You're not just solving the problem in front of you. You're thinking about how it scales in the future.
Exactly.
But what about byte and short? I mean, they might not be as common in your day-to-day coding, but they definitely have their uses.
Absolutely. Think about things like low-level file input-output or working with huge arrays where, memory is really a concern. In those situations, every byte you can save makes a difference. So like embedded systems or high-performance computing where you've got massive data sets, even saving a few bits per element adds up when you're talking about that kind of scale. And it can even help with cache locality, which can really boost performance.
Oh, interesting. So in those tight memory situations, they become really valuable.
Exactly. And it's also really important to remember those boundary constants for these types,
Yeah.
like integer.mivalue and integer.appsValue. Senior engineers, they need to know those limits inside and out to write truly robust code.
Yeah, because that's how you avoid those sneaky overflow or underflow bugs, right? And it's super important for writing good unit tests, making sure you cover all those edge cases.
Totally. Those boundaries, that's where bugs like to hide. Now, what happens when even a long isn't big enough? Well, we've got BigInteger.
Right, for those really massive numbers.
Exactly, like cryptographic keys or, calculations where you need absolute precision. Long just won't cut it there. You risk introducing silent errors. BigInteger gives you that arbitrary precision. But you got to remember, there's a performance trade-off. Every operation with BigInteger has some overhead. So it's something to keep in mind, especially in performance-sensitive systems. It's all about trade-offs, right? And as a senior engineer, you're always juggling those trade-offs to choose the right tool for the job.
Performance versus precision. The classic balancing act.
Exactly. Now, another thing that's really fundamental about Java is its machine-independent integer type ranges. Write once, run anywhere.
The heart of Java's portability.
Right. And it's a huge advantage over languages like C or C++, where the size of an int can actually change depending on the hardware. Java's design, it emphasizes portability and consistency. That machine independence, it might seem basic, but it's so valuable in distributed systems or when you're moving between platforms. It's one less thing to worry about, one less potential source of weird bugs.
Definitely takes a lot of headache out of the equation. So when we're actually writing these integer values in our code, we use the L suffix for long literals, like 400,000,000,000,000.
But there's no special syntax for byte or short literals, is there? You typically have to use casting like byte 127, which kind of tells you that, int is often treated as the default integer literal type.
Interesting. Now let's talk about different number systems. We've got hexadecimal literals, starting with 0x, like the famous 0xk for babe, and binary literals with the 0b prefix, where 0b1001 represents 9 in decimal. Understanding these is really helpful for low-level programming.
Oh, absolutely. And anytime you're working directly with bit patterns, hexadecimal, it's essential when you're debugging and looking at memory addresses,
Oh.
or dealing with color codes where each hex digit corresponds to a specific bit sequence. And, when you think about network protocols, data serialization, even interacting with hardware, knowing binary and hexadecimal is a big plus. It helps you understand what's going on at a much deeper level.
So they're good tools to have in your belt. Now, here's something really important to remember, especially if you want to avoid some nasty surprises in your code. Octal literals. Those are the ones that start with a 0.
Yeah, those can cause a lot of confusion.
Exactly. For instance, 011 in octal, that's actually 9 in decimal. So, it's probably a good idea to just steer clear of octal literals altogether. It helps keep your code clean and avoids any unexpected behavior. When you're working on a team, writing clear and understandable code is so important, and minimizing those potential gotchas, that's a key responsibility for senior engineers.
Couldn't agree more. Clarity and maintainability are crucial. And even something as seemingly small as using underscores in number literals, like 100,000 0 0 is 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0, it can make a big difference in readability.
Oh, yeah.
The compiler ignores them, but for us humans, it makes those big numbers much easier to read, which in turn makes the code more maintainable.
For sure. All right, let's get a little more advanced and talk about interpreting signed integer values as unsigned. This is when you need that extra bit for non-negative ranges. So a byte normally goes from Nevis 128 to 127, but if you're only working with positive values, you can treat it as 0 to 255.
Right. A bit more of a niche concept.
And the thing is, while basic arithmetic might work fine within those bounds, for other operations, you often need to use specific methods like byte.tone boats in B or the unsigned division and remainder methods in the integer and long classes. Is this something you only use in very specific situations?
Yeah, it's a more specialized technique. You wouldn't see it every day in typical application code. But understanding it shows you really get how numbers are represented at the binary level. And it can be super useful in those performance-critical scenarios where you need to squeeze out every bit of efficiency. It also comes up when you're working with certain data formats or in network programming where unsigned bytes are pretty common.
So it's about using the full potential of those bits when you know you don't need the signed bit.
Exactly. Think about a byte. It's 8 bits. When it's signed, that most significant bit tells you whether it's positive or negative. But if you treat it as unsigned, that bit becomes part of the value, essentially doubling the positive range you can represent. This is especially relevant in network programming or when you're working with binary protocols, where data often comes in as a stream of bytes representing unsigned values. If you misinterpret a signed byte as an unsigned one, you'll end up with incorrect data.
Yeah, you could get some really messed up values.
Exactly. But the key is to be really careful and not accidentally do sign arithmetic when you should be doing unsigned, and vice versa. It requires careful attention.
Okay, let's shift gears and talk about numbers with fractional parts. Floating point types.
Right.
In Java, we have float and double.
And as you know, double gives you much more precision than float. It provides about 15 significant decimal digits, whereas float only has 6 or 7. This difference comes down to how much storage they use. 4 bytes for float and 8 bytes for double. Back in the day, float was more common because memory was limited, but these days, with memory being more plentiful, double is usually the better choice. You don't want to be limited by the lower precision of float unless you really have to.
Makes sense. So the main reason to use float nowadays is when you need to store a ton of floating point values, and saving memory is super important. And then we've got the F suffix for float literals like 3.1f and the optional D suffix for double literals. And it's worth mentioning hexadecimal floating point literals too, things like 0 by 1.0 p10. The p there means the exponent is a power of 2 instead of the usual base 10. These literals give you more direct mapping to the way floating point numbers are actually represented in binary, according to the IE 754 standard. This level of precision can be really crucial in low-level programming or high-accuracy numerical work, where even tiny errors from converting between decimal and binary need to be avoided.
Yeah, so for like hardcore numerical analysis or low-level system stuff, they can be super useful. They offer a very precise way to represent those numbers. Now, it's also important to talk about those special floating point values, double dot positive infinity, double dot negative infinity, and double dot nan. These can pop up when you do things like divide by zero or take the square root of a negative number. A good engineer knows how to handle these edge cases gracefully.
Absolutely. Robust code anticipates these kinds of situations. And a really important thing to remember about NaN is that you can't compare it using the equals operator. You have to use double dot INNX. And there are similar methods, double dot is infinite and double dot is finite, for checking for those specific states. This all comes down to the IEEE 7-4 standard that governs how floating point arithmetic works.
Exactly. And here's a crucial point, especially for folks working on financial systems. You generally don't want to use float or double for precise financial calculations. This is because of round-off errors that happen because of how decimal fractions are represented in binary. So for example, 2.1.7 might not give you exactly zero point 0.3. In these situations, big decimal is the way to go. It gives you arbitrary precision without those pesky round-off errors. This is essential knowledge for senior engineers working on applications where numerical accuracy is absolutely critical. It's also a common topic in interviews to test your understanding of this.
Yeah, it's a really important distinction, especially when you're dealing with money. Knowing when to use big decimal instead of double shows experience and attention to detail.
Exactly. It demonstrates that you understand the potential pitfalls and how to avoid them.
Okay, let's move on to the char type.
All right.
So char represents code units in the UTF-16 encoding that Java uses. While you might not work with char directly all that often, you will see character literals, which are enclosed in single quotes like J. This character has a Unicode value of 74, which is also 4A in hexadecimal, and you can also use the U prefix followed by the hexadecimal Unicode code unit, so U Cedar Liro 4A is also J. This shows how Java can handle a huge range of characters from different languages. For example, U263A is the white smiling face. Now, UTF-16 is a variable width encoding, which means that some characters take up more space than others. This could have implications for string manipulation and storage, especially when you're dealing with text in multiple languages.
Yeah.
And finally, we have those common escape codes like N for a new line, key for a tab, and how to escape single quotes and backslashes.
Yeah, those escape codes are super important for working with text and making sure your output is formatted correctly.
Right. Lastly, let's talk about the Boolean type. Pretty straightforward. It has two values, false and true. And importantly, in Java, Boolean isn't a numeric type. There's no automatic conversion between Boolean and numbers like 0 or 1. This strictness helps prevent a whole category of errors that you might see in languages with looser type systems. Java keeps it clean and explicit.
Exactly.
Yeah.
It enforces type safety and avoids any weird implicit conversions.
So just to recap, for everyone out there gearing up for senior level interviews, we talked about signed integers, byte, short, int, long, and big integer, floating point types, float, double, and big decimal, char for Unicode characters, and the very distinct Boolean type. The takeaway here is that you need to show a deep understanding of these fundamental types. It's not just about knowing their names and sizes. You need to be able to think critically about how data is represented, the potential pitfalls, and how to make informed decisions about data types. This has a direct impact on system performance, how well it scales, and the integrity of your data.
Definitely. And when you're in those interviews, think back to your own projects. Were there times when choosing a certain primitive type or maybe not understanding its limitations had a real impact on how the system behaved or performed? Thinking about those experiences will help you connect these basic concepts to the more complex topics that come up in senior level interviews.
Absolutely. It's all connected.
Yeah.
Having a solid grasp of these fundamentals makes it so much easier to understand those higher level concepts like data structures, algorithms, even system design. A senior engineer understands that even the smallest details, like picking the right primitive type, can make a huge difference for the entire system. It's not just about knowing what these types are. It's about understanding why they exist, when to use them, and how to use them effectively to build reliable and efficient systems.
Yeah, that kind of nuanced understanding, that's what sets a senior engineer apart.
So as you prepare, dig into those fundamentals, connect them to your own experiences, and you'll be in great shape for those senior level technical interviews. Thanks for joining us for this deep dive.
It was my pleasure.